I think we'll just. Okay, yeah, so maybe we just
in the book of abstract or somewhere, I was listed as dictionary. Is that some other or but I mean, I thought nonsense. Or I mean, I did Google it. I mean, so these are the abstracts, and this is what the yeah. Yes, no, I know how to do anything.
I think, yeah, so we need to probably we need to focus this.
So why does it list Prada as
I don't know. This all these guys are left who were doing it.
it's some type of
Okay, so
well, I was wondering, like maybe
okay, well, yeah, so maybe we start now.
Sit here. No, you can do this one. Krishna knows on how to use that.
Okay, so yeah, it's a long day and it's the last lecture of the long for today. Mahesh K from ISA Rampur. Now he's going to speak on prime ideas of higher residue decay. Yes.
Can you minimize that one so that the whole slide is visible? It's a long day. We have decided to cut down the 4 days into 3 days so that fourth day we can go for it up to 3. So I really apologize for this long session that we have for these 3 days. Yeah, please.
Hello everyone. I would like to thank the organizers for giving me opportunity to work, to pursue my work. This is joint work with my supervisor, Dr. Prem Prakash Pandey. The title of my talk is Primary is Higher Residue Degree.
So you can you have to point here.
No, that will work. Just do it once here, up and down. That. Wait. Yeah, now you try.
Outline of my talk are the following: a statement of the main theorem. Then the theorem, that will be the main theorem of my talk. Then I will introduce some notations and basic definition. After that, I will introduce some theorems which we prove. These theorems are needed to prove the main theorem. After that, I will sketch the proof of the main theorem. Then there will be some differences. So we explore the ideal classes of unramified prime ideals with fixed residue degree of greater than 1 in the class group of number fields. As a consequence of this study, we prove the following theorem. This is the main theorem of my talk. So this theorem says that suppose n and m are two relatively prime integers greater than 1. Assume that n is relatively prime to Pm, where P is Euler-Tosin function. Then there is no cyclic extension L over cube degree n, which class will be cyclic of order n. One can obtain several corollaries from theorem 1. For example, let L over Q be a cyclic extension of degree 3 and P is converted to 2 mod 3 be a prime. Then the class number of L cannot be P. So here n is equal to 3, n is equal to 3, and m is equal to P, P of the form 3P plus 2. So 3 is relatively prime to P as well as 3 is relatively prime to P minus 1. So from theorem 1 we get that the class number of L cannot be P. So let's see one more corollary. Let L over Q be a cyclic extension of degree 5 and let P be a prime not converted to 0 or 1 mod 5. Then the class number of L cannot be P. Similarly, one can easily check that 5 is relatively prime to P as well as relatively prime to P minus 1. So from theorem 1, we get that class number of L cannot be P. Now we see one more corollary which is the following. Let L over Q be a cyclic extension of odd degree n. Assume that the class number of L is of the form P square where P is a prime number. If n is relatively prime to P times P minus 1, then the class group of L cannot be cyclic. So here m is equal to P square and n is relatively prime to P times P minus 1. So n is relatively prime to P square as well as n is relatively prime to Q of P square. So from theorem 1 we get that class group of L cannot be cyclic. Truman proved that the class group of cubic cyclic field L of Q zeta 163 is isomorphic to Z by 2Z, that's in Z by 2Z. This result we get easily from corollary 3. Now I will introduce some more notions and basic definitions. So for any number field L, we use OL to denote the ring of integer of L, and CL denote the class group of L. And we use HL to denote the class number of L. Let's see the definition. Let L over K be an extension of number fields and P be a prime ideal of L lying above the prime ideal P of L. So OL is the ring of this number field L, and OK is the number field of OK is the ring of integer of K. And this P is the prime ideal of OL, and this prime in the prime ideal of OK. With this relation, P is equal to P intersection of OK. Then OL by P is a field, and OK by P is also a field. So one can check that OL by P is a finite dimensional vector space over OK by P. So the degree of this field over this field is called the relative ratio degree of this for the extension L over K. We denote the relative ratio degree of P for the extension L over K by FL of K of P. Truman proved that for any prime number L, the class group of Q zeta is generated by the ideal classes of prime ideals of residual degree 1, where zeta denotes in primitive ideals of unity. But for a general number of period, a much stronger result is known. This result says that if L is any number field L, then each ideal class of L contains infinitely many prime ideals of L of residual degree 1. But there are no such results for the primary higher residual degree. Prem Prakash wanted to explore the following problems. He wanted to determine the extension L over K of number fields for which there exists a positive integer greater than 1, such that the ideal classes of unramified prime ideals of L of relative residual degree generate the class. In relation to this problem, he defined the following set. This set can be defined for any extension of number fields. I am taking here L over K Galois extension. So we say that a natural number F is an element of RLK if the class group of L is generated by the ideal classes unramified primes P of L such that the relative residual degree of P is equal to F. So here L over K is a Galois extension. So if you take any prime ideal P of L, the relative residual degree of P divides the degree of L over P. So we find that the RLK is a finite subset of L because a number has finitely many divisors. Now we check that RLK is a non-empty set. So let's see theorem 2. Theorem 2 says that if L is any number field, then each ideal class of L contains infinitely many prime ideals of L respectively. So this means each ideal class of L contains at least one unramified prime ideals of L of ratio degree 1. It means that the class group of L is generated by the ideal classes of unramified prime ideals of ratio degree 1. So from this theorem we get that 1 is an element of RLQ. But residual degree in tower extension is multiplicative. If you take a prime ideal P in L, then relative residual degree of P this extension is equal to the relative residual degree of P for this extension over P times relative residual degree of this P for this extension. So left hand side is 1. So this implies FL of P is equal to 1 for any prime ideal P of L. So from here we get that 1 is an element of RLQ. It doesn't matter whether K is Q or not, but RLQ is always a non-empty set. So we say that the set RLK is non-empty if it contains an element other than 1. Before proceeding further, now I will introduce some more notations. I will use GLK to denote the Galois group with Galois extension L over K of number fits. For any group G, out of G denotes the automorphism group of G. Now I will introduce some theorems which we proved. These theorems will be used to prove the main theorem. So let L over Q be a cyclic extension such that class number of L is relatively prime to degree of L over Q. Suppose there exists an element sigma in GLQ. GLQ is a Galois group of the Galois extension L over Q. So that any homomorphism psi from GLQ to automorphism group of class group of L maps sigma to the identity automorphism. Then each divisor of the order of sigma is an element of RLQ. So see, if sigma is an identity element, the order of sigma is 1, and if you take any homomorphism psi from Galois group L over Q to the automorphism group of class group of L, then psi maps identity to the identity element. So psi of sigma will be the identity automorphism. So from here we get that one is element of RLQ whenever the class number of L is relatively prime to the degree of L over Q. So as a consequence of this theorem, we obtain the Kummer seizure. Whenever the class number of digital is relatively prime to L minus 1. So let us recall again what is the Kummer seizure. For any prime number L, the class group of digital is generated by the ideal classes of prime ideals of digital of restrictively 1. So we can always find such a sigma if suppose there exists a divisor f of degree of L over Q, such that f is relatively prime to the order of the automorphism group of class group of L. Then this hypothesis will follow automatically. So we will see that in next theorem. That theorem can be easily derived from this theorem. L over Q is cyclic extension such that the class number of L is relatively prime to degree of L over Q. L over Q, if there exists a positive divisor f of degree L over Q, which is relatively prime to the order of the automorphism group class of L, then each divisor of f is an element of R. So let's see the proof. L over Q is a cyclic extension, and f divides the degree of L over Q. And so that GLQ is a cyclic group. So corresponding to each divisor, there is an element. So we can find an element sigma of order f. And let psi be in any homomorphism from Galois group L over to automorphism group class group L. Then order of psi of sigma divide the order of sigma, and order of sigma is here, and psi of sigma is an element of the automorphism group class group. So order of psi of sigma also divide the order of the automorphism group class group. But we are given that f is relatively prime to the order of the automorphism group class group. Okay. So it forces that order of psi of sigma has to be 1. So this implies that psi of sigma is the identity automorphism. Now theorem follows from it. Now we prove our main theorem. Let us recall the theorem. So suppose n and b are two relatively prime integers greater than 1. Assume that n is relatively prime to p, then p is equal to z. Then there is no cyclic extension available to dpn such that the class group of L is cyclic of order n. If possible, suppose there exists such an extension L over Q of degree L such that the class group L is cyclic of order N. So class group L is cyclic of order N, it means that class group L is isomorphic to Z by N. And we know that for any integer M greater than 1, automorphism Z1 Z isomorphic to Z1 Z star. Z1 Z star is the set contains all the natural number T from 1 to M which are relatively prime to M. So we obtain that Tm is the quantity of the automorphism group of class group of L. But we have assumed that n is relatively prime to Tm. So we obtain that n is relatively prime to the order of the automorphism group of class group of L. And also n divides the degree of L over Q. Of course, n is because n is the order of the degree of L over Q. Now applying theorem for F is equal to n. So theorem 4 says that we are taking here F is equal to L. So we have seen that F divides the degree of L over Q. So there will be F is equal to N. So n divides the degree of N over Q, L over Q, and n is relatively prime to the automorphism group class group L. So each divisor of n is an element of RLQ. So in particular, n is an element of RLQ. So we obtain that n is an element of RLQ, but by the definition of RLQ, so it says that the class group of L is generated by the ideal classes of unramified prime ideals of residue degree L. Right? But we know that the prime ideals of L of residue degree N are principal because n is the degree of L over Q. So if we take any prime integer, that would be their inner. So this implies that class group is trivial. That is HL is equal to M is equal to 1, which is not possible because we have assumed that M is greater than 1. So this shows that such an extension L over Q does not exist, and we complete the proof. These are the references. Thank you.
So any questions?